The name of my institute is Copernicus Center, so this is Copernicus. And I would like to talk about Sinus H3, and this is recent work I did with Ranjiv Misra from Ayuka in Pune, India, and Marek Gieliński, who used to be at Durham in England, but now he quit astrophysics and now is working on DNA in biology at Dundee University because he couldn't get a tenure track position in the UK, and his specific wish was to stay in the UK. He was not willing to move to any other country, and I think it's great pity. So this might be one of his last work. I would first give an introduction on high-mass X-ray binaries, and then go to describing what I think is peculiar about Sinus H3, and then how we can explain this peculiarity. Why is it different from all other X-ray binaries? And why are high-mass binaries interesting? Many very exciting objects are in this class, and high-mass binaries are objects in which the companion is of high mass, and Sinus H1, Sinus H3, Vera, SS433 are all high-mass binaries. And a couple of years ago, there was discovered the first eclipsing black hole binary in M33 galaxy, in which the black hole mass was quite high, about 16 solar masses, and the donor mass was 70. And then, some years ago, TeV emission was discovered from binaries, and all of the TeV sources, all of binaries emitting TeV are high-mass X-ray binaries, so there is something about high mass that makes this to be related to TeV, and in fact not a single low-mass X-ray binary being discovered either in TeV or in GeV. And those are young systems which ages of millions of years rather than billions, which also makes them, for some applications, they are interesting. And then classification of those high-mass X-ray binaries is here, and first we can classify them with respect to the compact object. It can be the neutron star, and most of high-mass X-ray binaries have neutron star, or a black hole, and we have only a handful of black hole high-mass X-ray binaries which are listed here, and then perhaps ULXs also have black hole, some of ULXs or many, but this is an open issue. And then we can classify them with respect to the supergiant, and the known high-mass binaries have either OB, supergiants, BE, or Wolf-Rayet. And then mode of accretion. The standard one is stellar-winged, and I think those are objects that are treated by stellar-winged, but then in some cases we do have Rorschach overflow, for example in SS433, and this Rorschach overflow in such high-mass system leads to huge luminosities. And then another mode is a disk around a B star. B stars are B stars that rotate very fast, and this rotation leads to formation of a disk, which is not an accretion disk, but decretion disk, in which mass flow out rather than in, and then when the orbit is eccentric, the neutron star can cross the disk, and then there is an enhanced event in this BE X-ray binaries. And then magnetic field of the neutron star, in all known cases except one, we have high magnetic field, 10 to the 12, and therefore many of them are X-ray pulsars. The only exception known to me is Sinus H1, in which we certainly know it's a low magnetic field because the system shows X-ray bursts, but however, the issue whether this is a high-mass or low-mass binary is still unresolved. The most recent paper claimed it's a high-mass, but we still don't have an ambiguous determination of the companion.
But this X-ray burst was observed only once.
Yeah. So, I mean, I would say Sinus H1 is another peculiar object in which, so maybe it's even, some people say it's a black hole, I don't know what, but I think, so this is an open issue, what is Sinus H1, so I don't want to spend too much time on it.
So usually we can distinguish neutron compact object is neutron star or black hole.
Yes, we can. Very
How
easily.
to judge?
Well, there are many.
Mass and the size?
First, many systems have mass function. Like, for example, signal 6.1 has mass function, and then we know the mass, the classification of the companion. We know more or less inclination, and then from that we determine the minimum mass of the compact object. And in that case, it's about, I think, 7 solar masses. So for realistic calculations, and then therefore it's a black hole, and also for M33H7, this is very well determined mass. And then for other systems, we just look at characteristics of the system. The black hole binaries have very characteristic spectral states, for example, and timing behavior, etc. And so we have so-called black hole binaries and black hole candidates. And black hole candidates are those in which we are convinced that they are black holes, but we don't have direct mass determination. But
just mass is too large.
And too large for yeah, I mean, like this M33H7, they determine the mass of the compact objects from kinetic, from velocities of the system to be 16 solar masses. So this cannot be a neutron star.
What are the errors for that system?
For M33H7, those are actually less than 1 solar mass. I forgot the numbers, but
well, if it's eclipsing, it should be very precise.
Yeah, it is very precise, because the previous high mass system was GRS 1915, with which it was 20, it was 14, but the errors were like plus minus 3. Mm-hmm. And here I think the errors, like, they claim errors of 0.5. I mean, I forgot the number, but certainly they claimed this was the first accurate determination of that. I will actually talk later about another system in which also there is even higher mass. And then another way to classify those systems is where does the high energy emission come from? And in most cases it comes from accretion. However, we know at least one certain case in which high energy emission is from collision between stellar wind from the B star with pulsar wind from a young pulsar, and this is this PSR B1259, and most likely also LS1 plus 61. If we consider binaries in general, we can also think about binaries without a compact object, and this is this, for example, the subject of last week's seminar, Eta Carinae, which seems to be the first binary with colliding stellar winds emitting GeV discovered. And in that system we have two very high mass stars. One is 100 solar masses, another 30 solar masses, and then the collision of the two winds gives emission in GeV range observed by both Agile and Fermi. Now about the black hole high mass X-ray binaries, they are in general, if we can look at X-rays, they are very similar to low mass X-ray binaries, and the main difference is that they have persistent emission, and the persistence of emission is due to accretion by wind. In low mass X-ray binaries we have disk instability in which accretion is via low accretion rate, very low accretion rate Rorschach overflow, and then we have accumulation of mass over some years, and then we have some kind of ring which then undergoes this hydrogen opacity instability in which there is a sudden flow, and this is an X-ray nova. On the other hand, all known high mass X-ray binaries with black holes are persistent. And as I said before, in general, properties are very similar in high mass and low mass binaries, X-ray spectra and spectral states of Sinus X1, and for example, this is a low mass X-ray binary, are very similar. So what happens in inner disk seems to be not really feeling what happens in the outer disk. And now Sinus X3. This is a very luminous radio source and also X-ray source, and in radio it undergoes outburst. It has this jet which at some point can be the brightest radio source on the sky, I think 20 Zdziarski, which I think is quite high for radio sources. And it has very low period of 4.8 hours, and this is unusual for high mass binaries, which have usual periods more of some several days or more. And And the donor is a Wolf-Rayet star, and this is the only known X-ray binary in our galaxy with a Wolf-Rayet donor. And it seems that this low period is related to the fact that this is a Wolf-Rayet. The system simply, the contracted, the compact object, which is most likely a black hole, was originally at much longer orbit, wider orbit, and then it contracted because of the huge wind rates. This wind may it's 10 to minus 5 solar masses per year, or maybe even more, and then it is a very, very strong wind in which slows down the companion, the compact object. And then it's very strong extinction. The donor is actually invisible in optical light. X-rays are strongly absorbed, and the X-ray spectra in general similar to black hole binaries, which I show in a minute, but differ quite strongly in some details. And also the power spectrum is very peculiar. It has no power above 1 Hertz or even less, while in typical black hole X-ray binaries or neutron star X-ray binaries, low mass X-ray binaries, we have a lot of power above 100 Hertz. So these two facts require explanation. And then one issue is what is the mode of accretion, and this is what I calculated some while ago, that this is the radius, this is standard radii of Wolf-Rayet stars, shown here, and this is the radius of the black hole, of the Roche lobe of a black hole companion and neutron star companion. We are not completely sure what is the companion, and see in both cases the helium Wolf-Rayet star easily fits within the Roche lobe, so accretion is via stellar wind. And this is what I said about this similarity and differences between spectral states. This is a black hole binary and a transient, which shows canonical spectral states, and these spectral states are, for example, this one ultrasoft, in which we have domination of X-ray emission by accretion disk. What is plotted here is energy per log of energy flux per log of energy of photons, which is so-called nu f nu. So a maximum on this plot corresponds to maximum of emission, actually. So in this ultrasoft state we have accretion disk emission, and then we have some varying strength of a high energy tail, like the tail can be here, or it can be even here, and then we have this so-called low hard state in which the high energy break is usually at about 100 keV, and it corresponds to electron temperature in cognizing plasma also of this order, and this is seen in many objects, like in Cygnus X1, and the characteristic temperature seems to be due to solution of hot accretion disk. Already in a paper by Shapiro and Menelda in 1976, that they found the characteristic temperature of hot accretion disk is 100 keV, and therefore we have this high energy break. Now when we look at Cygnus X3, we actually have fairly similar states, right? This ultrasoft, it has a lot of absorption here, so this is very strongly absorbed, but this is only external absorption. But then it seems to have this very similar ultrasoft state with some kind of tail here, and then it also has some states like this high state in which there is a strong disk emission and then some weak tail and then a strong tail from a peak. But then when we go to something that looks like the low hard state, there is one peculiarity, that this peak is at 20 keV rather than at 100 keV. And this is the only object that we know with such a low peak energy, and when we fit it by thermal cognization, we get temperatures of a few keV, 4 to 8 keV, which is very peculiar for that system. And there was a long debate what is actually the nature of this low hard state, whether this is some, what is causing this peculiarity. And as I said, the other peculiarity is the lack of signal at high frequencies. So how to explain this? This can be explained, we propose, by Compton scattering. And if we have a Thomson thick medium, then this can dump variability at high frequencies simply because of scattering. When we have a photon varying at say some rate of 100 Hz, when it goes through a Thomson thick cloud with optical depths of a few, there will be a distribution of travel time for escape, and then any periodic signal would be strongly damped. So basically we can reduce the power spectrum at high frequencies. And on the other hand, due to Klein-Shira effects, if we scatter hard X-rays, we can move the energy break from 100 kV to 20 kV by Compton downscattering, and at low energies, the energy is much less than 511 kV, the Compton scattering is coherent, but at 100 kV strongly incoherent, so a photon loses a lot of energy in a single scattering, so both effects can reduce both effects can account for this peculiarity. So we have lack of variability and the peak, the difference, the peak. In addition, this system also shows interesting energy-independent orbital variability of X-rays, and this is due to some medium that is fully ionized. Like in Sinus X1 we also see orbital variability, but this is due to absorption in the wind, and absorption in the wind would preferentially absorb soft X-rays. The bound-free cross-section is much stronger at soft X-rays than hard X-ray, while here, if we look at different energy bands from 100 kV to 1 kV, we see more or less same amplitude of orbital modulation, which can also be explained by Compton scattering. The cross-section between 100 kV and 1 kV is more or less constant, and thus the same medium can modulate the flux. So now our specific calculations, what is plotted here, it's this red and blue arrow bars give the data, and we consider two types of hard state, and this is this peculiar. You see both are pitched below 20 kV. On the other hand, we assume some intrinsic spectrum, which is plotted, for example, here or here, which has a much higher temperature, and then this is downscattered, and in general there is this equation, considering the number of scattering in a cloud, that the peak after downscattering would occur at 511 kV divided by square of the Thomson optical depth, roughly independently of the beginning of the seed photons.
What narrow feature in several?
Oh yeah. Okay, good question. This is an iron K alpha line, which is not explained by this model, but this iron K alpha line comes externally of the source. This is emission most likely from the stellar wind. So we have, in addition to this ionized cloud, we do have stellar wind, which is not fully ionized. It has iron is not fully ionized, and therefore it has emission of iron K alpha. So in fact, details at low energies we cannot reproduce by this model, in particular K alpha, because any K alpha would get very much downscattered by this optic-lytic medium. However, there is a lot of emission outside, which we actually see in different lines in spectroscopy.
But didn't you say you had a temperature for the scattering medium of the order of a few keV or something like that?
No, in this case the temperature is assumed to be 0. The first
but where did this few keV come from? You mentioned that.
Sorry, what few keV?
The temperature of the plasma.
Oh no. So this is this is the observed spectrum, right?
Yes.
And if you say that this is intrinsically produced, you can fit it by thermal quantization, and you obtain 4 to 8 kV. This type of spectra, assuming they are intrinsic, would require a temperature of a few kV, which is very different from typical hot plasma in black hole binaries, which is at 50-100 kV. However, now we say
it's only the radiation temperature.
Yeah. But now we say this is a artifact of scattering. This is after scattering. So our beginning, this is what we assume. This is our initial spectrum, and it is at much higher temperature.
But your initial spectrum is not thermal component spectrum because it has some edges and.
Well, this is thermal comptonization plus reflection.
But it has huge reflection.
Uh,
And it's already absorbed, right? Because
yeah, this is already absorbed due to sort of technical issue how to reproduce the spectrum, because there is some type of complex absorption, so we introduce the same absorption to account for the observation. Well, our goal was just to reproduce this spectrum.
Yeah, just I don't understand why you don't try to model the iron line together, because I mean, if your medium is cool, right? You would have, it will not be fully ionized, so fully ionized. You will have K alpha emission anyway in the medium, and you will have a huge line and edge.
Actually, you would have an edge, but the point is that in the observation you don't see a huge edge.
But you just showed there was a huge line and edge there.
Where?
In the data that you showed.
In which data?
In this on the right.
Pardon?
On this one on the right, there was a huge edge there.
Where where
At least in the softer state, is clearly it's built.
No, but when you look at the hard state, it's very difficult to say whether there's an edge. I would say there's.
It's just
weaker.
together with the line.
Together with the line, yeah.
Yeah, and in the soft state you clearly see the edge because it's the huge edge at 9 kV, right, or whatever.
Yeah. No, in the soft state you do, but in the hard state, the conclusion of actual detailed modeling by Ania Szostek of the Reposar's data show that there is not such a huge edge. No, but I agree that the conclusion of previous work was that the iron line comes from the stellar wind, not from intrinsic to the source. And what we assume indeed relatively strong reflection, but I think this is not so important because it gets smeared over anyway. I mean, I could model it without reflection because the final spectrum here is, doesn't show edges or reflection features. The final spectrum is comptonized by Thomson depth of 5. And of course, we could also try to account for some iron line if we assume it's not fluorinized, but I guess then we would get a very strong edge if we assume that this medium is not completely ionized.
Mm-hmm.
But I mean, I would try to go to next step in which you can show that it cannot be not fully ionized in a moment.
So from down scattering, the cold medium gains energy. So you lose plenty of energy from the photosynthesis.
Yeah, this is a good point. This would, exactly. This is the next step. I mean, we just start now to reproduce the spectrum. So what this have? This is our intrinsic spectrum, and then what is shown by these dots, or in this case they are completely identical to the data, is the Comptonized spectrum. In this case, we just show an effect of increasing the temperature of initial spectrum, and then this is a divergence. This is just to show that we don't get, we have to sort of fit the initial temperature to get what we get, because if we make it too high, the slope, the peak is still at this value, but then the slope at high energies is higher. So in this case, the data disagree with the model. In this case, the data agree with the model. And this is another set of data in which also the points agree with the model. Except, of course, in all cases, we do not reproduce the iron complex because we assume it's external to the source. But I agree with you that this medium would gain energy, and this is a very good point, which we'll then address. Then but in the meantime, we consider timing, and this is the same. We use it for that. We use a Monte Carlo code to come from here to here. We use a Monte Carlo. So now we use the same Monte Carlo to find the Green's function for timing, and the question is how much a photon emitted at the center of the sphere spent in the source, and the distribution of this time is shown here. This is the dots are Monte Carlo data, and this is the distribution, and this starts at 5, optical depth of 5, because the minimum, the time is measured from the center of the sphere, and of course the minimum time spent in the sphere can be tau of 5. I mean, you cannot get it out. So this is just the surface of the
What do you
sphere.
mean tau of 5?
From the
What is tau here?
tau is the optical depth of the sphere, Thomson optical depth.
But this is time.
But we measure time in Thomson units. So time and optical
What's
depths
that?
are the same.
This is
Pardon?
the mean free path, you mean?
Lambda.
Yeah, right. So
this
one
is
unit
the-
of time is mean free path.
Okay.
So tau of 5, the minimum time is when a photon escapes without scattering. It just goes to the surface and it takes
Again, yeah.
5 units
So
of
basically
time.
you have optical depth 5, so your mean free path is 1. So you
Yeah, the
have-
mean free
you-
path
you
is
have-
always 1. Right?
Okay, so you have 5.
5 mean free paths. We measure time.
five
We
units
we
of
don't
mean
want
free
to
path.
measure time in seconds because this would be very model
I mean,
dependent.
normally people measure time in light crossing time of the whole source, not of the mean free path.
Well, but this would introduce
Dependence on tau.
dependence on tau
But it's
because
still a tau dependence. So
yeah, I mean this is just technical issue. It just what you of course you could measure it from in light crossing time, but then but this has the advantage that this is advantage. I mean this is both the time spent in the sphere in units of Thomson time and the tau covered by a photon. A photon scatters multiple times, and then you can measure the optical depth along its path, and this is that. But of course, you can divide it by 5 and then get it in units of.
multiply. On what divide?
Yeah, I mean you can divide at this
Divide
scale.
by
Yeah,
five,
I mean
yeah.
the 80 would be 80 divided by 5. Yeah, this would be 16 light crossing time. But anyway, what we see here is an exponential dependence at high time, and then there is a break here, and this is what we fitted this Green's function by this formula, which is actually this red curve, and it's a very good fit, and then this term accounts for photons that escape without scattering. I mean, some photons escape without scattering, and then we have to take, and then these are Green's function, so then to get attenuation at a given frequency, we take Fourier transform of this function, and then after taking Fourier transform, we take absolute value, and square of it would give attenuation of the Paul spectrum. Right? And then this is previous result, or actually somewhat improved result. Lightman, Rybicki, and Lamp in '81 computed the number of scattering in a sphere, and however they assumed infinite optical depth. I mean the limit of very large optical depth, and this is what is obtained from their calculation. Actually, convolved with the Poissonian distribution of the time spent in the sphere, which makes some improvement.
But that was paper by Suniev Titarchuk in 80, right? 1980, where everything was done.
No?
What do you know? What exactly? No.
You mean that this function was obtained?
I don't remember exactly which function was obtained there, but in
No,
Suniev
not
Titarchuk
this
there are all
function.
kind of functions were obtained.
Yeah, they obtained all kinds of functions. In fact, as pointed out by Lightman, Rybicki, and Lamp, in '81 paper they made a mistake and they missed one crucial term for the case of a sphere. So I use result of 1 year after that, of Lightman,
But, I mean, if you have optical depth 5, isn't it the typical number of scattering is 25, tau squared?
Yeah, it's 25 over 2,
Okay, over 2. Okay, so
12.5.
12. And so it should be 12, and this means that in these units it should be, the peak should be at 12, which is about there, yeah? Which is probably about there.
Yeah, right. Yeah. But this is now relatively broad, because when we plot it per tau, but you actually should plot it per log of tau, and then multiply it by tau to get fractional contribution from different regions, from different intervals of time, but we just wanted to have something that is a straight line because for purpose of plotting. We plot this is exponential function because this axis is logarithmic and this axis is linear, so then we have a straight line, but if you look for contribution of different times, this would be one more power of tau, right? So anyway, this is a Green's function, and then we calculated for a number of optical depths and fitted those coefficients. And this is a Fourier transform, square of the absolute value of Fourier transform, and this gives the attenuation, which at low frequencies there is no attenuation, but then there is a cutoff, very sharp cutoff introduced at certain frequency, and then attenuation goes to e2 minus 2 tau, because the number of photons that escape is e2 minus tau, and square of that is e2 minus 2 tau. So this leveling gives you e2 minus 2 tau, and again this frequency is measured in Thomson units.
Yeah, and because we have sharp cutoff artificial at low tau, you will have some high frequency noise there that is not physical. Yeah?
You mean the assumption of a sharp, right?
Yeah, because you have sharp cutoff in your sphere, so there is a at low tau, you'll have a jump in your function, and therefore if you make Fourier transform of that, you'll have the high frequency.
Yeah, good question.
Something which is completely unphysical.
Right, but
so this tail there, it's meaningless in reality.
Right, but we didn't use it for calculations, and I agree with you that, and also there is one subtle point out where you calculate the distribution of times for a sphere, that in fact the distribution of times at the sphere surface is not equal to that measured by distant observer, because if you have a photon that escapes radially, it goes straight to the observer, but if it goes tangentially, it would be additional one radius covered by that photon. So there is some kind of spreading introduced also by the shape of the sphere. But I agree that of course we should do calculations for some profile of density to make it more realistic, but since we are interested in the cutoff, not in this leveling, then we didn't do it for this application. But I mean, certainly a good point that this high frequency, but this high frequencies for this tau of 5, it's anyway such a low level that we cannot measure it anyway. So, but for this particular model, it's correct. So now we look in the size of the scattering cloud, and we found that actually we get a characteristic break frequency that is somewhat different from, it's lower than 2 over tau square, because since the number of scattering, average number of scattering is tau square over 2, when you take 2 over tau square, you will get characteristic frequency in, again, the same units, and then you would expect a cutoff there. However, the distribution is relatively broad, and you get a lower break, you get 4 times less, and then from that we obtain this formula in which the size of the source is given by this, and this 2 would be in the numerator normally, but it's in the denominator in our results, in which gives us the size of the cloud. So what we found, the size of the cloud is actually, and the break is at, the cutoff in the data is at 1 Hertz, so this gives us 3 to the 9 centimeter. And this is much less than separation between the two stars, which is 3 times to the 11. So it means that radiation from the star has negligible effect for cooling of this cloud, because our original, my original idea was that since there is this huge Wolf-Rayet star, it would cool down the cloud, and the cloud would still be cold in spite of receiving energy. However, this is not true, and the cloud will be heated, and then we look at equilibrium temperature of this cloud, and we found it is actually 3 keV. And this is our final result. So this is assuming Compton downscattering at temperature of just cold electrons and the 3 keV, and I think at 3 keV they will be completely ionized, anyway. I mean, there is no chance to get any kind of iron features from plasma at 3 keV, which is in additional, very strongly irradiated. We calculated this ionization coefficient is 3 times 10 to the 4 plus 3 keV temperature. So I don't think we can get any iron emission from that. And now we fitted the same thing and we get optical depths of 6.5 because some photon gets now upscattered, not only down scattered. Before it was 0 temperature, now it's equilibrium. And so this means that this spectrum and this spectrum have the same power. This looks slightly lower because it's also absorbed and we didn't plot unabsorbed. But the two within about 10% accuracy, the two have the same luminosity. And now we found that the temperature of this plasma is 30 keV. So the comptonizing original source has temperature of 30 keV, which is slightly less than what I said before, 50 to 100 keV. But I will go to this point in a minute. And this is now this is the Pearl spectrum. And this cutoff that I mentioned is just this lack of power above 1 hertz. And if we assume that this cutoff is due to downscattering, we get the size again, and the size is actually in this case 2 times 10 to the 9 centimeters. The size is slightly smaller because the optical depth is larger. So if we assume that this high energy break is due to downscattering, we can determine all the parameters. And now the parameters, the final parameters are here. The optical depth of the cloud is, as I said, about 6, temperature about 3 keV, the size 2 times 10 to the 9, and the intrinsic source has 30 keV, and optical depth about unity. And then we look at another object, at the black hole binary, at similar luminosity. The intrinsic luminosity is 10 to the 38 Hertz per second, which is actually much more than the hard state, for example, of Cygnus X1, which is 10 to the 37. So when we look at comparable luminosities in this system, we actually found identical temperature. We fitted 30 keV to the hard state of G839-4 at the same Eddington ratio. And then, if the black hole is tensor masses, the Eddington ratio is accounting also for the fact this is a helium, so Eddington luminosity is higher than in hydrogen. It's several percent, and this is completely typical for black hole binaries. So we can basically get the system to become a normal standard black hole binary if there is in addition this cloud. Now the question is, what is the origin of this cloud? And these conclusions are here that we can account for all these properties, and then this cloud cannot be due to the stellar wind. The stellar wind scale is 3 times to the 11, while we have 2 times 10 to the 9. But we think it is either accretion disk wind, or actually some kind of bulge that is formed by the collision of the stellar wind with the disk. The disk is likely to have small size, that this is a wind accreting system in which the size of the disk is not the Roche-low, but is much less than that. In fact, in all high mass X-ray binaries, the disk seems to be relatively small. So if the size of the disk in this system is a few times 10 to the 9 centimeter, then the bulge would be of the similar size, and this bulge would account for that. And indeed, this is basically the only high mass binary with wind which shows such high accretion rate. If we look at all other black hole binaries accreting from wind, they have at least accretion rate that is, sorry, not accretion rate, the mass loss rate from the companion 10 times less, and the separation that is 10 times more. Like Cygnus X1 has separation of 3 times 12 centimeter, and accretion rate and mass loss rate from the companion 10 times more. So then the density of the wind at the black hole in Cygnus X1 is 1,000 times less than in this system. So the fact that this scattering cloud is seen here but not in other systems is accounted by the very high density of the wind at at the black hole. And then this bolometric luminosity in the hard state actually favors the presence of the black hole, because we still do not have a mass function. So then, now the final slide is about two other binaries discovered in recent years with Wolf-Rayet companions, and each probably contains a black hole, and this is actually a very interesting system, IC10X1, which is an eclipsing system, and again they could determine the mass of the black hole from kinematics, from the mass function, and they determined it between 23 and 34 solar masses, and this is actually the current record holder for the black hole mass. And luminosity is several times 10 to 38, but Cygnus X3 also has this luminosity in other of its states. So this is an extragalactic analog of Cygnus X3. And then another system with a Wolf-Rayet star, NGC 300X1, has even higher luminosity and similar orbital period, but we don't know the mass function, but it may also contain a black hole. So it might be that this Wolf-Rayet systems have high mass black holes, and the fact that the black hole mass is so high, maybe as a speculation due to the fact that it accreted hypercritically at some stage from the wind of the companion. The companion underwent very dramatic ejections in the history, and some of that could be accreted by the black hole. And this would explain this relatively high black hole mass in this system. So thank you.
So how much can you accrete? So the lifetime is of those systems if they are accreting. So
well, this was an idea of Van den Heuvel, and he actually estimated that it all depends how whether you can accrete hypercritically or not. I mean, this is this issue, because if you have very optically, if you have trapping of photons, you can accrete. The system radiates it into luminosity, but you accrete.
So if the accretion is limited by Eddington, then you cannot accrete so much. But if you can accrete 100 times more, then that's fine.
Yeah. I mean, this was an old paper, I think, in the 70s, by Van den Heuvel about this.
Okay. Interesting. Any more questions?
I mean, if you have a massive Wolf-Rayet star, the companion star which has collapsed, you have had a mass even larger than that, and to keep it bound, don't you have to accrete most of it into the black hole? You can't lose a lot of the mass. In that case, that will split up the system.
You mean that if this ejection goes to the space, the black hole will become unbound? Or?
No, the whole system will disrupt. Well, you have to lose half of the total mass, yeah? What's the limit?
Yeah,
So
I guess so.
I mean, if you start with the companion should be more massive than the survivor one. One going into the black hole, so don't you need to accrete most of it into the black
Let's
hole?
say if you take 50 solar mass original star and 20 mass companion, 20 solar mass companion, then if you make a black hole only 10 solar masses.
Oh yeah, but
You
you
will
Might this be the reason
have much more. I mean, 20 solar masses.
Yeah, but maybe 10 is accreted afterwards. It was 15 to start with, let's say.
Well, we have black holes with 6 solar masses.
No, but the question is that it has to be, now together this mass should be larger than the lost mass, right? Otherwise it would be different.
Yeah.
Exactly.
So okay, if it's 25 in the black hole plus whatever is in the companion, another 20. So you could lose maybe 20, 30 solar masses.
I think for this particular, for this IC10H1, I think they estimated the mass of the companion to be the present mass is 16 of the Wolf-Rayet star. So maybe it was, I don't know, 25 in the beginning, and this black hole was 6.
Or 15.
If you assume that the if you assume that the iron line is produced farther away, even, that should be like no variability or different variability. Looking at the first plot, I saw that this line seems to change with different accretion states.
Well, it does, but the iron line is actually produced by the photons from accretion. The iron line is the wind is irradiated by the photons from.
Yes,
And
but
then
so
therefore you should have.
But these are
You
just
should
few
respond.
seconds. These are
Okay.
just seconds, 10
So
seconds, 100 seconds, or
So
10
it should
seconds.
respond directly
Yeah,
to,
it,
the,
just,
to the changes
it
of
does
the
respond
photons.
to irradiation, but it should not have variability by its own because it's a
Yeah.
large. But if you change irradiation, you can have a huge loss and which can still have variability, right?
So it's interesting if you say that it's a bulge around the accretion disk, right? With the size of the accretion
Yeah.
disk, and it certainly should be not spherical. It should be some
Yeah.
asymmetric. And
Like-
you have the X-ray source around the black hole,
Yeah.
let's say, and then this asymmetric cloud.
Yeah.
Probably this would, this would make your orbital variability, right? Because
Yeah, but we do
you will
see-
have the cloud which
Yeah.
is with the
Mhm.
surface flux different
Yeah.
on different directions.
Yeah, this was our idea that this, we do see orbital modulation by about 50%. I mean, the flux goes up and down by a factor of 2 during a single orbit, and then this may be accounted for by different optical depths in.
It means that
different
it should be the flux should be higher when this bulge is behind the black hole, when is the black hole in front of you, yeah?
Yes.
Because it's the
Yeah,
cloud.
but this is the standard
thinner,
situation,
and this
yeah?
and this is consistent with that, yeah.
Well, we do not have ephemeris for
For Cygnus
for Cygnus X3, but I think it's completely consistent. I mean, usually people,
No, but
even
we should
without.
have, because there are plenty of lines, so we should be able to see when you have strong absorption in lines. Right.
Mm,
So you should be able to know when is what is the geometry of the system.
yeah, I think that I must admit maybe I don't know, but there was certainly the discussion that these lines that are observed may come from different parts of this warfare wind,
Mhm.
and therefore because when you have a system in which all lines come from the surface of your companion, that there is no problem. But this wind is very very thick,
Yeah.
and then they have a problem.
What is the distance between the Wolf-Rayet star and the black hole?
3 times 10 to the 11.
And the radius of the Wolf-Rayet star is,
A few, I mean,
so it's really at the base, very close where the wind is accelerated. Or
yeah.
you had this
Yeah, this is I mean, we don't know the radius, but this is sort of standard idea of Wolf-Rayet.
yeah.
So you think if this
And
is a wind,
where's the black hole here?
Yeah.
This is the Roche law.
That's the rope.
Oh, the Roche, right, the Roche, yeah.
But where?
The black, no, if you just apply Kepler's law, then assuming total mass of 50, you get 3 times 10 to the 11
What?
centimeter.
The separation. No.
Separation, yeah.
So it's.
So one solar mass,
the-
one solar radius is 7 times to the 10, right?
Mm. It's not 10 to the 11.
So it is, yeah.
So it's a few times the.
Yeah, so they, let's say, the radius is about 10 to the 11, so the separation
What
is 3
is-
times the radius.
We estimated the optical depth of the wind
0.5.
But that what do you use for the mass loss rate from the Wolf-Rayet star?
No, actually, there was a paper that my student did on estimating the optical depth, the mass loss rate from the wind using X-rays and X-ray spectroscopy, and that she got about 10 to minus 5, and then the Thomson depth of the wind, the average Thomson depth of the wind from the black hole to the observer was 0.5.
Why is the temperature 3 kV? How the cloud cools?
Oh, the cloud cools by, well, I mean, by Compton upscattering. So we have this, we have this is an intrinsic spectrum at the center of the cloud, and this is the outgoing spectrum. So in equilibrium, the two have to be equal.
Yeah, I mean, you're continuously putting energy into the cloud.
And continuously get it out.
Yeah,
So
how?
this is what you put
What's
out,
wrong
and
with
this
surface?
is,
It's just
yeah.
escapes
So,
from another
so
surface.
some of photons get upscattered. So this 3 kV gives you some upscattering, and then upscattering cools the plasma, right? If you would have pure downscattering, you would keep heating it.
But if it's a wind that escapes, then further out it cools, would you expect some line cooling? I mean,
Yeah, I
when
mean
the
you do,
temperature
but
drops,
we
from adiabatic cooling, I mean,
no, we didn't. We just assumed that these two have to be equal. That what you put in should be what is out. But in fact, there are plenty of lines from sinus H3, and this analysis is very, messy. And then you have this stellar wind, which makes it very complicated. So
What was the luminosity, the X-ray luminosity?
10 to the 38.
38, so it's quite a bit lower than that of the Wolf-Rayet star.
Yeah, the Wolf-Rayet star is probably 10 to the 39, but I would say anything between 10 to 38 and 10 to 40 is unknown, and because it's it's obscure. The peak of it's wind, everything. But if it's 10 to the 39, this is 1%. The size is 1% of the separation, so it gets 10 to minus 4. The radiation by the star is 10 to minus 4.
Okay, so it's...
So this was my original idea was that it could be low temperature because it could be cold. Pardon?
It couldn't be any self-induced wind from, because of the heating. We have the heating by the X-ray source on Wolf-Rayet star, that would evaporate, could evaporate
No.
some stuff. Well, it's been discussed, it was discussed for the X1 a long time ago. It's self-induced winds. I mean, if you're putting in more energy than the star is radiating, then of course it will affect the wind.
Yeah.
But probably, I mean, the solid angle is fairly small.
Yeah, the solid angle, I think, I'm pretty sure that what star receives in X-rays is much less than intrinsic luminosity.
Yeah, okay. But then it should not.
Yeah. I think it's unlike, remember one case, Fourier 1820, minus 30, in which the X-ray radiation was 1 million the intrinsic luminosity. But here it's...
I still have troubles with your plot. This was new, right?
Yes?
I mean, if you cool down some photons and then upscatter the other portion of photons, then approximate area where you gain energy should be equal to the area where you lose energy, and it doesn't say that.
Right. This actually, if you look at that, this is 25% more. However, this is absorption. This is shown the absorbed spectrum.
So there is something on the left-hand side.
Yeah, I mean,
Paolo should continue.
this is very strongly absorbed. So I should have the plot perhaps unabsorbed. Then they are equal. Because this is external absorption. This is something that gets absorbed between the cloud and us in the stellar wind and also in the interstellar medium. But the idea is that the of course, the two areas should be the same.
And what's the optical depth for external absorption?
The NH, we use NH for that 4 times 10 to the 22 centimeters. So Thomson depth is low, but this is bound-free absorption. So it's very strong absorption. 4 times 10 to the 22 is very strong.
Where's the cutoff in imaging? At a few kV? Or?
Yeah. I think so. Yeah. I mean, I think everything, everything below the
that
iron
cutoff
line.
is due to the
This is absorption.
That's the trouble with this source, that is so strongly absorbed that it's difficult to see what's happening there.
Come back to this, the size of the Roche lobe. Was, do you take the radius of the Wolf-Rayet star just, was that from observations or was it from,
From some other papers. No, this
so
was
this
a
is just a
standard.
theoretical radius relation?
Yeah, theoretical
Yes.
based on
Was this
model,
I
of
thought
observations.
that was fairly uncertain, so I was just wondering, I mean, you're fairly close to the Roche-low actually. It's,
The threshold of neutron star is high up.
So it's about 80%,
Yeah.
well 75% of the
Yeah.
Roche-low. And
Yeah.
I thought the errors in the radius could
Yeah,
be at
no,
least as
right,
large
yeah.
as that. So is there any argument why it can't be filling the Roche-low?
I think if they were filling, the Roche-low would get huge, would get some kind of SS43 system. I don't know. I mean, with this.
Yeah, I'm just wondering whether that would be a possibility.
No, I would say no. I agree with you that given uncertainties, but I thought no.
I mean, there are things like instabilities in these Wolf-Rayet stars
We
which
don't know
haven't been included
For
in this
example, we
hydrostatic.
don't know anything for the rotation of the Wolf-Rayet star. If we had some kind of tidal loading,
Yeah.
for example, we could say something.
No, I mean, I agree that this is a very uncertain subject. I just don't know.
So we don't know much for the Wolf-Rayet star itself.
No. I mean, in '92 there was a Nature paper by Van Kerkwijk et al. In which they announced it's a Wolf-Rayet based on lines, but the parameters of this star is highly uncertain. I mean, I would say the only thing wanted to show that it's possible that it's not a Roche-low overflow and it's wind aggression, but
But being so close, it should be quite affected by the gravity, and it should not be spherical, really. So it's
maybe. I mean, but how do you tell whether it's spherical or not spherical?
no, that's a problem.
Okay, any more questions? No? Okay, then let's thank Andrei for a nice talk.